All right, so here are some important logs to remember. The first two you can probably reason through on your own by writing them in exponential form, so those aren't really too important. The really important ones are these bottom two. And the bottom two are true because of what's written over here. Log base b of x and b of x are inverses. So you remember when you do the composition of inverses, it equals x? So in this first one, they put b of x in for x right here. And you get x, of course, because when you put inverses, when you do a composition of inverses, you get x. Same thing down here, they put log base b of x in for x in this one. Of course, whenever you do that, you get x. So those two bottom ones are going to be very handy. The two top ones are handy, but like I said, if you forget those, you can sort of reason through them. But you need to commit this to memory, that log base b of x and b of x are inverses. All right, here are the first four we're going to do today. We are just going to simplify these expressions using those rules that we just learned. So using the rules of inverses, the inverse properties. What? I would write this down. Just giving you a second to write it down. All right, so for those first two, it looks sort of like this property, right? You have a base, and then you have a log in the exponent, and the base of that log is the same as your base. So, do you see how b in this case is just 4, right? So 4 log 4 of x. Well, if this is the rule, and I wrote it like this, I just replaced all the b's with 4's, what would the answer be? It's the same thing as right here. X. We're just using that property that you just learned, but instead of b's, it's 4's. Instead of b's, what is it in number 14? 8's. And instead of an x, it's a 10. So what's our answer? 10. You need to use this rule. If you're not using this rule, you're not going to get this. Okay. Do you see how b to the log base b of x equals x? So this is basically saying if you have a base and there's a log in the exponent that has the same base, your answer is just whatever came next. So here we have 8 to the log 8. So our answer is just whatever comes next. It's kind of like the 8 and the log 8 cancel and leave you with whatever was in the argument of that log. Questions? Here is the next rule that you wrote down on the last page. Just a reminder for you. It was log base b of b to the x. So now you have a log with a base. And you're taking the log of that same base to the x. Now, this is one that you can sort of reason through. I'll show you off to the side on the board. If you have log base 6 of b, whoops, I'll change it to 6, sorry, of 6 to the x, right? That's the problem. Everyone agree? I just rewrote number 15 over here on the board. I'm going to set it equal to some variable w. I want to know what w is, right? I want to know what this whole expression is. Well, I could write it in exponential form like we did yesterday. So this is actually 6 to the w equals 6 to the x. So if I'm solving for w, what's w? X, right? If the bases are the same, the exponents have to be the same. So if you draw a blank here, always write it as exponential, and you can sort of reason your way through it on some of these. Some of them it gets a little trickier. It's easier to just remember. So the answer for number 15 is x. Number 16 is a little tricky. What's the problem right now with 16? Yeah, the base of the log is not the same as this number. Like right here we had log base b of b. We need this to be of 3. Well, can you think of a way to write 83 that involves the 3? 3 to the third is 27, but you're on the right track. We want it to have a base of 3. 3 to the fourth. 3 to the fourth and 81 are the exact same thing. Everyone agree? So I'm going to rewrite log base 3 of 81 to the x as log base 3 of 3 to the fourth to the x. Now, what happens to the log base 3 of 3 part? Yeah, and what are you left with? 4x. Your answer here is 4x. Now, again, this is one that you could change to exponential, get the bases to be equal, which forces the exponents to be equal as well, like I did on number 15 off on the sideboard. If you're interested in that, try it. Let me know if you need any assistance. If not, I will just assume you understand. Sort of, yes. Remember that log the base, it's like saying this to what exponent would give us this? That's what a logarithm is. We learned that yesterday when you rewrite it as exponents. So 3 to the what would give you 3 to the 4x. It's obviously 4x. So they don't really cancel, but when you rewrite it, you can see that they're sort of equivalent, and it just leaves you with the 4x. I wouldn't get in the habit of thinking of them as canceling, though, because it's not like every time you see the same number in a logarithm, they're gone. It doesn't really work like that. Sometimes it does, but not always. Other questions on this one? All right, the next thing we're going to look at is graphing logarithmic functions. This is in your book. It's a little different in your book. They do not do a lot with transformations. They just have you memorize different formulas. I think it's easier to start with the most basic formula and then just think of what your transformations are doing it. The book and I disagree a bit there. So if you look in the book, it'll be a little different, but you should still be able to graph. But I'm going to always do them this way. So I'm going to start with the basic graph, y equals log base b of x. Right away, I know the following things. I know that x equals 0 is my vertical asymptote. So when we were doing exponentials, we had horizontal asymptotes. The x-axis was our horizontal asymptote. Now we have a vertical asymptote, and it's actually the y-axis. The domain is all the positive x values, and the range is all real numbers. This is the complete flipped version of exponentials. Remember, in exponentials, domain was always all real, and then the range is the one that sort of went up and down depending on transformations. Now, the reason everything seems a little backwards here is because, remember, log base b of x is the inverse of the graph b to the x. Remember, inverses flip across the y-axis. Or sorry, not the y-axis, the line y equals x. And I'll show you a picture of that on the next slide. So this is basically taking everything we've been doing with exponentials and sort of flipping it. Now, what you learned about the b value is going to be the same. This is when we were learning about whether it's an exponential growth or an exponential decay. If b is positive, your graph should be going up as you move to the right. If b is, if it's positive, it's greater than 1. If it's less than 1, it should be going down as you're moving to the right. And then here is what's a little different from the book. I want you to always start with these two features and then think of how your transformation will change those. So transformations, of course, can change our domain and our asymptotes. The range on all of these should stay all real numbers. All All right, this is what I was describing for you with our inverses. So you all know how to graph this by now. This is what we did last week. So in this example, it's 2 to the x, but really it can be anything to the x. We graph these by plugging in 2 points one day, 5 points one day, just a couple points. Right around the origin, we'd always plug in -2, -1, 0, 1, 2, and then we'd get the graph. Today what we're going to do, we're going to use that graph to graph logarithmic functions because they're inverses. Remember, inverses, they just flip across this line, the y equals x line. If you're doing it with a table and you're finding the inverse, the x's and y's just flip. So we're going to graph exponentials today, and then we're going to take them back to logs by flipping the x's and the y's. This is actually our first example, I believe. So I'm going to give you the problem, y equals log base 2 of x, and we are going to use what we know about y equals 2 to the x to graph it. Any questions on the basic idea of what we're doing today? All right, here it is. So a lot of people don't really know mathematically why they're inverses, so I'm just going to show you really quick. You don't really need to write this down. It's not super important, but it is kind of nice to know where this comes from. So if I was going to rewrite this using exponential, I'd start with a 2, then I'd have the y as my exponent, and it would equal x. Everyone agree that those are the exact same thing? Okay. Now, if I'm looking at the equation and I want the inverse, what do? You switch the x's and the y's. So this is actually 2x equals y. So if I can graph this using a table, then I would just swap the x and the y values. That would give me a graph for this. Questions on that idea? Now, a lot of people don't go through all these steps every time. They just remember that for the inverse, this is going to be your base, this is going to be your exponent. Question?
Why can't we keep it 2y instead of that and then switch it?
If you wanted to graph this, you wouldn't have to switch it at all. This is the same as what we started with. I just wrote it in a different form. So yeah, if you want to graph this, plug numbers in for y and then get x's, that would be fine.
Like, how come you don't know?
Because I like to use the property that they're inverses, because this is something that I've been graphing for 2 weeks now in this class.
Okay.
So I know that the inverse is, it's still going to be a y equals and a y equals, and we usually graph things that are in y equals. The base is our new base, and then this is going to be our exponent. So here's the table. And remember, I'm not going to graph these points because this isn't going to be my answer. This is going to be the inverse of my answer. So I'm just going to plug in those 5 points right around the origin. So -2, -1, 0, 1, 2. And I am just taking 2 to that power. So 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the negative first is 1/2, 2 to the -2 is 1/4. Remember, because you have to take the reciprocal when you have a negative exponent. Now, that's something we did last week. Everybody feeling good about that? That should not be anything new. You should be quick with those by now. Now, my graph, the log graph, is just the inverse of that. How do I find the inverse of something when I have a table? Switch them. So now my x value is 1 and my y value is 0. I have 2 and 1. I have the point 4, 2. I have the point 1/2, -1, and I have the point -4, -2. And that gives me that graph. What are your questions on this idea? This is getting to be like what I would consider upper level algebra skills. So let me know if I'm losing you somewhere. Domain for my second table and the graph. So what are the input values? What are the x's? I don't see any negative x's.
Greater than 0.
Yeah, your domain are all the x values greater than 0. Your range is what's all real numbers. So it's kind of the flipped version of those exponential domain and range. Remember, domain was always all reals. Range is the one that would change depending on our transformation. It's the opposite here. You can plug in only positive numbers, but you can get out negative numbers. What are your questions on this? All right, here is number 18. So what's the inverse of log base 1/2 of x? Other way. Yeah. The inverse is going to be, remember the base goes to your base and your argument goes to your exponent. So if I can graph y equals 1/2 x and then flip the x's to y's, the y's to x's, that will give me this log graph. So I'm going to plug in those same basic 5 points. Anything to the 0 is 1. 1/2 to the first is 1/2. 1/2 to the second is 1/4. A negative exponent will cause us to flip it, so now we'll have a 2, and then flip it and square it, you'll have a 4. I'll give you a second to catch up. All right, now the graph that I actually want is the inverse of this. So I'm going to make all my y's x's, all my x's y's. 1, 0, 1/2, 1, 1/4, 2, 2, -1, and 4, -2. Domain, what do you guys think?
X greater than, you get greater than 0.
Yep, x greater than 0. It's always going to be x greater than 0 unless you had a transformation when you're dealing with logarithms. And then the range is all real numbers. Let me know what your questions are. All right, here is number 19. What's ln? I forgot. Yes, it's called the natural log. What's the base for a natural log? E, very good. So this is the inverse of e to the x with a transformation in there. So let's deal with the transformation at the very end. So I'm going to forget about the plus 2 for now. I'm going to deal with it later. I just want to graph y equals the natural log of x, which is the inverse of, what's the base? E. It's the inverse of e to the x. So I'm going to graph y equals e to the x, then I'm going to take the inverse, then I'm going to do the transformation. Sounds fun. All right, e to the x, we did a bunch of these already. Since we're pretty familiar with e to the x, I'm going to take it down to just 2 points. If you want to do more, that's fine. But remember, exponentials all have the same basic shape once you sort of figure out where the asymptote is and whether it's an exponential growth or an exponential decay. So when you plug 0 in, e to the 0 is 1 and e to the first is 2.7. You would do that on your calculator, or you would just know it by now because the value of e is 2.7 something, something, something. Now, if you want to do more terms, you can. It's up to you. If you want to plug a 2 in there, that's fine. If you want to plug a -1 in, that's fine. It's really up to you. Any questions on how I got these points and where I'm going with it? All right, now I want the natural log of x. So I need to take the inverse of e to the x. So now what's going to happen? Switch them. X's become y's, y's become x's. Now, adding 2 to your x. So this is in parentheses. This is part of the input. What does that do to your graph? Thank you. So when it's in parentheses with the x, it moves it up is when it's outside. When it's in the back, not next to the x. Well, not in parentheses with the x. This one moves it left. It's the opposite when it's inside with the x. Remember, if it's plus, you're going left. If it's minus, you're going right. So we want to move all the points to the left 2 units. The way you move to the left is you subtract 2 from the x values. So now I'm going to take these new x values and I'm going to subtract 2 from them. Those are the points I want to graph. Now, if you're not really sure what these look like, you might want to do a couple more points than just 2 because you won't really know how the curve goes or if it's just a straight line through these 2 points. So if you want to graph 3 or 4 until you get used to it, that's fine. Or you could think of, well, e to the x, I know looks something like this, and it's an inverse with a transformation, so it's going to have that same shape but a mirror image across the y equals x line and then moved a little bit. But there's a couple different ways to reason through that. All right, what are your questions? I know this is a sort of long process. We good? Is your hand up? No? Okay. What's the domain? The domain is usually all the x values greater than 0, but I moved everything to the left too. Greater than -2. Since you moved everything to the left 2, now your domain has to also move to the left 2, so it's the values greater than -2. Your range stays all real numbers. The range has not changed. What are your questions? All right, here's number 20. Again, it's a natural log with a transformation. So the first thing you want to do is forget about the transformation. The next thing you want to do is figure out how you're going to get some points. So if I forget about the transformation, I am just going to graph y equals The natural log of x. Natural log of x is the inverse of what function that we can easily graph? Y equals e to the x. So I'm going to graph y equals e to the x because it's super easy. I already have the table from the last slide. Then I'm going to take its inverse. That'll give me the natural log of x. Well, I already have that table from the last one as well. Now we'll apply this transformation. Is that in parentheses with the x, or is it something that you would do at the end? You'd do it at the end. So is this going to move it left, right, up, down? Down. This moves it down 3. How do you move something down 3? You subtract 3 from the y's. So that new table, the natural log of x, I need to take it down 3 notches. So I'm going to subtract 3 from every y. And there's my graph. I'll give you guys a second to catch up. I know that was a lot. You should have those first 2 tables, though, from the last example. Which is nice, right? Because you have a take-home quiz. So if a natural log example shows up, you already have the e to the x in your notes. You already have the log x in your notes, or natural log of x in your notes. So you would just have to do whatever transformations are there if you've taken good notes. If not, it will be on YouTube. You can watch it. All right, domain. Did we do anything to our domain or our x values? No, so it just stays greater than 0. Our range is all real numbers. If you move all real numbers down 3, it's still all real numbers, so nothing really changed as far as domain and range. What are your questions on this? All right, here's your homework tonight. I am going to start class tomorrow by doing homework questions on the board. However, once I hand your quizzes out, my mouth is shut until the quizzes are collected. So don't think you're going to just ask me for help on the quizzes. I will not do them on the board. I will not answer anything. You have all your notes. You have your books. You have your internet. You have your friends. You have graphing calculators. You have many, many, many resources to help you with the quiz tomorrow. I am not one of them. So if you want homework questions, we'll do that before the quiz. Once the quiz is out, I am a closed book.